Earthquake epicenters occur mostly along tectonic plate boundaries, and especially on the Pacific Ring of Fire. Global plate tectonic movement. An earthquake is the shaking of the surface of the Earth resulting from a sudden release of energy in the Earth's lithosphere that creates seismic waves. Earthquakes can range in size from those that are so weak that they cannot be felt to those violent enough to propel objects and people into the air, and wreak destruction across entire cities. The seismicity, or seismic activity, of an area is the frequency, type, and size of earthquakes experienced over a particular time period. The word tremor is also used for non-earthquake seismic rumbling. At the Earth's surface, earthquakes manifest themselves by shaking and displacing or disrupting the ground. When the epicenter of a large earthquake is located offshore, the seabed may be displaced sufficiently to cause a tsunami. Earthquakes can also trigger landslides and, occasionally, volcanic activity. In its most general sense, the word earthquake is used to describe any seismic event, whether natural or caused by humans, that generates seismic waves. Earthquakes are caused mostly by rupture of geological faults but also by other events such as volcanic activity, landslides, mine blasts, and nuclear tests. An earthquake's point of initial rupture is called its hypocenter or focus. The epicenter is the point at ground level directly above the hypocenter. Three types of faults: A. Strike-slip. B. Normal. C. Reverse. Tectonic earthquakes occur anywhere in the Earth where there is sufficient stored elastic strain energy to drive fracture propagation along a fault plane. The sides of a fault move past each other smoothly and aseismically only if there are no irregularities or asperities along the fault surface that increase the frictional resistance. Most fault surfaces do have such asperities, which leads to a form of stick-slip behavior. Once the fault has locked, continued relative motion between the plates leads to increasing stress and, therefore, stored strain energy in the volume around the fault surface. This continues until the stress has risen sufficiently to break through the asperity, suddenly allowing sliding over the locked portion of the fault, releasing the stored energy. This energy is released as a combination of radiated elastic strain seismic waves, frictional heating of the fault surface, and cracking of the rock, thus causing an earthquake. This process of gradual buildup of strain and stress punctuated by occasional sudden earthquake failure is referred to as the elastic rebound theory. It is estimated that only 10% or less of an earthquake's total energy is radiated as seismic energy. Most of the earthquake's energy is used to power the earthquake fracture growth or is converted into heat generated by friction. Therefore, earthquakes lower the Earth's available elastic potential energy and raise its temperature, though these changes are negligible compared to the conductive and convective flow of heat out from the Earth's deep interior. There are three main types of fault, all of which may cause an interplate earthquake: normal, reverse, and strike-slip. Normal and reverse faulting are examples of dip-slip, where the displacement along the fault is in the direction of dip and where movement on them involves a vertical component. Normal faults occur mainly in areas where the crust is being extended, such as a divergent boundary. Reverse faults occur in areas where the crust is being shortened, such as at a convergent boundary. Strike-slip faults are steep structures where the two sides of the fault slip horizontally past each other. Transform boundaries are a particular type of strike-slip fault. Many earthquakes are caused by movement on faults that have components of both dip-slip and strike-slip. This is known as oblique slip. Reverse faults, particularly those along convergent plate boundaries, are associated with the most powerful earthquakes, megathrust earthquakes, including almost all of those of magnitude 8 or more. Megathrust earthquakes are responsible for about 90% of the total seismic moment released worldwide. Strike-slip faults, particularly continental transforms, can produce major earthquakes up to about magnitude 8. Earthquakes associated with normal faults are generally less than magnitude 7. For every unit increase in magnitude, there is a roughly 30-fold increase in the energy released. For instance, an earthquake of magnitude 6.0 releases approximately 32 times more energy than a 5.0 magnitude earthquake, and a 7.0 magnitude earthquake releases 1,000 times more energy than a 5.0 magnitude earthquake. An 8.6 magnitude earthquake releases the same amount of energy as 10,000 atomic bombs of the size used in World War II. This is so because the energy released in an earthquake, and thus its magnitude, is proportional to the area of the fault that ruptures and the stress drop. Therefore, the longer the length and the wider the width of the faulted area, the larger the resulting magnitude. The topmost, brittle part of the Earth's crust, and the cool slabs of the tectonic plates that are descending into the hot mantle, are the only parts of our planet that can store elastic energy and release it in fault ruptures. Rocks hotter than about 300 degrees Celsius flow in response to stress. They do not rupture in earthquakes. The maximum observed lengths of ruptures in mapped faults are approximately 1,000 kilometers. Examples are the earthquakes in Alaska, Chile, and Sumatra, all in subduction zones. The longest earthquake ruptures on strike-slip faults, like the San Andreas Fault, the North Anatolian Fault in Turkey, and the Denali Fault in Alaska, are about half to one-third as long as the lengths along subducting plate margins, and those along normal faults are even shorter. Aerial photo of the San Andreas Fault in the Carrizo Plain, northwest of Los Angeles. The most important parameter controlling the maximum earthquake magnitude on a fault, however, is not the maximum available length, but the available width, because the latter varies by a factor of 20. Along converging plate margins, the dip angle of the rupture plane is very shallow, typically about 10 degrees. Thus, the width of the plane within the top brittle crust of the Earth can become 50 to 100 kilometers, making the most powerful earthquakes possible. Strike-slip faults tend to be oriented near vertically, resulting in an approximate width of 10 kilometers within the brittle crust. Thus, earthquakes with magnitudes much larger than 8 are not possible. Maximum magnitudes along many normal faults are even more limited because many of them are located along spreading centers, as in Iceland, where the thickness of the brittle layer is only about 6 kilometers. In addition, there exists a hierarchy of stress levels in the three fault types. Thrust faults are generated by the highest, strike-slip by intermediate, and normal faults by the lowest stress levels. This can easily be understood by considering the direction of the greatest principal stress, the direction of the force that pushes the rock mass during the faulting. In the case of normal faults, the rock mass is pushed down in a vertical direction, thus the pushing force equals the weight of the rock mass itself. In the case of thrusting, the rock mass escapes in the direction of the least principal stress, namely upward, lifting the rock mass, and thus, the overburden equals the least principal stress. Strike-slip faulting is intermediate between the other two types described above. This difference in stress regime in the three faulting environments can contribute to differences in stress drop during faulting, which contributes to differences in the radiated energy, regardless of fault dimensions. Comparison of the 1985 and 2017 earthquakes on Mexico City, Puebla and Michoacán/Guerrero, where plate boundaries occur within the continental lithosphere. Deformation is spread out over a much larger area than the plate boundary itself. In the case of the San Andreas Fault continental transform, many earthquakes occur away from the plate boundary and are related to strains developed within the broader zone of deformation caused by major irregularities in the fault trace. The Northridge earthquake was associated with movement on a blind thrust within such a zone. Another example is the strongly oblique convergent plate boundary between the Arabian and Eurasian plates, where it runs through the northwestern part of the Zagros Mountains. The deformation associated with this plate boundary is partitioned into nearly pure thrust sense movements perpendicular to the boundary over a wide zone to the southwest and nearly pure strike-slip motion along the main recent fault close to the actual plate boundary itself. This is demonstrated by earthquake focal mechanisms. All tectonic plates have internal stress fields caused by their interactions with neighboring plates and sedimentary loading or unloading. These stresses may be sufficient to cause failure along existing fault planes, giving rise to intraplate earthquakes. Collapsed Grand Hotel building in the San Salvador metropolis. After the shallow 1986 San Salvador earthquake, the majority of tectonic earthquakes originate in the Ring of Fire at depths not exceeding tens of kilometers. Earthquakes occurring at a depth of less than 70 kilometers are classified as shallow focus earthquakes, while those with a focal depth between 70 and 300 kilometers are commonly termed mid-focus or intermediate depth earthquakes. In subduction zones, where older and colder oceanic crust descends beneath another tectonic plate, deep focus earthquakes may occur at much greater depths. These seismically active areas of subduction are known as Wadati-Benioff zones. Deep focus earthquakes occur at a depth where the subducted lithosphere should no longer be brittle, due to the high temperature and pressure. A possible mechanism for the generation of deep focus earthquakes is faulting caused by olivine undergoing a phase transition into a spinel structure. Earthquakes often occur in volcanic regions and are caused there, both by tectonic faults and the movement of magma in volcanoes. Such earthquakes can serve as an early warning of volcanic eruptions, as during the 1980 eruption of Mount Street.
You say that I'm psychotic.